For the last couple of classes, we were trying to discuss about the cycloaddition reactions. We said like two unsaturated molecules can undergo a addition reaction to give you a cyclic unsaturated products, and based on cycloaddition reactions we said that cycloaddition reactions can be broadly classified based on the number of electrons which are interacting, and we broadly classified them as 2+2 cycloadditions and 4+2 cycloadditions, and we said that we will be discussing that in the coming classes. And so we started with 2+2 cycloaddition reactions. We said that 2+2 cycloaddition reactions on photochemical activations is suprafacially allowed, and if you do a thermal activation you get an antrafacial addition. In the case of antrafacial, we said that there is a limitation, and that is the geometry of the molecules. If it is favored, then you end up with the antrafacial reactions. And we said if we take a simple simple alkene system and do a photochemical activation, you end up with a suprafacial 2+2 cycloaddition reactions, but when you do the same reactions in thermal you do not end up with any product. So we did some we saw some good examples where we can get 2+2 cycloaddition reactions on photochemical activation, and they go by a suprafacial additions. When we went for antrafacial, we took ketene molecules and we saw that ketene geometry was nice. It undergoes a 2+2 antrafacial cycloaddition reactions, and with that we did many synthetic utility of your ketene chemistry. We tried to react with an alkene and we saw that we can think about getting a cycloketone systems. Then we did reactions with your aldehydes and we end up with a beta lactones. Then we carried out reactions with your amines and we got beta lactam system. So we studied in general how 2+2 reactions occurs. Then we said we will now what we will do, we will concentrate on our 4+2 cycloaddition reactions. The first reaction comes to your mind about 4+2 cycloaddition is your famous Diels-Alder reaction. So that is what we are going to concentrate on this class. So this is your Diels-Alder reaction. So you can have a 4 pi electron system, and you can, and there is a 2 pi electron system, your alkene, and this is your diene, butadiene with your alkene forms a nice cyclic product. You can have a substituent, end up with a substituent here. So this is your simple Diels-Alder reaction. Basically Diels-Alder reactions, Diels discovered this reaction in the year 1928 with his student Alder. I think this is the first reactions which has been kept based on the scientist's name who has discovered this reaction, and this is your Diels-Alder reaction. And the year 1950 they shared Nobel Prize for chemistry. They got Nobel Prize for chemistry in the year 1950 for Diels-Alder reactions. Diels-Alder reaction is a very like many important synthetic utility this reactions has. So what we will do initially, we will try to see the mechanism of the reaction and try to understand different components, how a diene should be, how a dienophile should be, what condition favors this reaction. All these things we will do in detail right now. Okay. So the first thing we will get into is mechanism. Nothing but a simple, you take a diene system having an alkene so you get a sort of transition state six-member transition state. Can think about this transition state very nicely, and this will give you a final product. Okay. If you carefully watch your diene is your 4 pi electron system and your dienophile is 2 pi electron. So, that is why we call this reaction as 4 pi plus 2 pi cycloaddition. Reaction. Okay. This is the simplest mechanism of Diels-Alder reaction. Just you take a diene which is your 4 pi electron system and you have a dienophile which is your 2 pi electron system. They form a type of cyclic transition state, and this cyclic transition state then gives you a product. Okay. Just clearly obeys your pericyclic principle, this reaction. Now, what we will do, we will see your diene, how your diene should be for the reactions, Diels-Alder reaction, how your diene should be favoring a Diels-Alder reaction, how it should be to favor your Diels-Alder, how your dienophile should be. So, we will do in detail. Now, we will start with your diene. Take your dienes. The first condition your diene should be, if you want the proper diene for carrying out a Diels-Alder reaction, is that it should be electron rich. Okay, that should be your first condition, that if a diene which is good electron rich will make your reaction nice, will favor your reaction, Diels-Alder reaction very nicely. Okay. The second important thing about diene is that diene should have a perfect geometry to carry out a Diels-Alder reaction. For example, if I take your dienes, I can classify them as open chain system like linear one, or we can call it as a open chain, or you can think about having an acyclic. Okay. So, how it should be? If I consider a open chain diene, for example, your butyl will take a open chain diene system. So, in open chain diene, if I take your butadiene for example, like so, this is the simplest way of your butadiene. How it exists? Normally, you can write two ways. Right. So, butadiene can exist like your transoid form and cissoid form. Okay. So, which should be which geometry it should be to do a Diels-Alder reaction? See, this is the preferred one to do a Diels-Alder reaction. It should be in cissoid form. Okay. In transoid form, that is a limitation if you talk about diene. See, the major limitation that it should be in the cis configuration or cissoid configuration to carry out your Diels-Alder reaction, apart being an electron rich. Okay. If it is in a transoid form, you never get this type of Diels-Alder reaction. Since it is a linear, you always have a equilibrium between your cissoid to transoid. If you have your transoid, you end up with a cisoid which undergoes a Diels-Alder reaction, not this one. So, cannot do Diels-Alder. This can do Diels-Alder reaction. Okay, that is the more important point of your open chain. So, the first we said that diene should be electron rich. After the second point we are talking about that the diene should be in cis configuration to do the reaction. You call as S-cis, right, cisoid. If it see in the case of linear, you have always an opportunity of your transoid and cisoid, and your cisoid ends up doing the Diels-Alder reaction. But once we go to acyclic system, for example, if I take an acyclic dienes, we will take two cases, like we will have a cyclopentadiene, furan, or cyclohexadiene. One of type, and another class you were talking, we can talk about this type of Declan system. If you see this class of dienes, that is your cyclopentadiene, furan, and your cyclohexadiene, that is your furan, cyclopentadiene, furan, cyclohexadiene. See, this type of dienes, if you see their conformation is locked, all these guys are S-cis, okay, and they are excellent diene for Diels-Alder reaction. They have excellent dienes for Diels-Alder reaction. But if you come to this class of diene, they are S trans, the conformation is locked in S trans, they cannot go for your cisoid form. So, their conformation is properly locked and they are in the S trans, and they cannot do Diels-Alder reaction. They are not good diene for Diels-Alder reaction. So, that is the thing about your diene. So, two things you have to keep in mind when you are thinking about your diene. One is that your diene make it electron rich. How you make a diene electron rich? Any idea? You can have your how you make a diene? Yeah, you can just attach your donor substituent to a diene like methoxy, like that substituent. If you attach your substituent to a diene, then it becomes like more electron rich. Once they are more electron rich, yes, you can do the reaction nicely. It can be a very good diene for the Diels-Alder reaction. That is the first point. It should be electron rich. The second important point to be remembered in your about your diene in Diels-Alder is that it should be S-cis, that is cisoid cisoid conformation. Otherwise, if it is in a trans conformation, you never get your Diels-Alder reaction. In acyclic system, yes, you know that there will be a equilibrium between your cisoid and transoid. So, acyclic system, in acyclic system you get Diels-Alder reaction, but in cyclic system, in linear system, but in acyclic system, the conformations are locked. If you have like trans, it never gives you a Diels-Alder reaction, but in linear you always have a equilibrium. So, you can think about Diels-Alder reactions there, clear. So, 2 points, electron rich, another is your S cisoid conformation. These are the two things you have to remember when you talk about dienes in Diels-Alder reactions. Okay. So, we are clear with this. Okay. Now, what we will do is that we will slowly move to the next substrate, that is your dinophile. How a dinophile in Diels-Alder reaction should look. As I said, first dinophile should be electron just opposite to a diene. So, your dinophile should be electron poor in nature, electron poor. They are considered to be very good dinophile for your Diels-Alder reaction. For example, if I take an alkene system, okay, this is a dinophile which can act for a Diels-Alder reaction, but I can make this as a better dinophile, just making it much more electron poor. You can do that. Yeah, in case of diene, what we did, you just attach your electron donor substituent, so that it becomes electron rich. In case of dinophile, you just go for your electron withdrawing substituents. And think about your electron withdrawing substituent. This is a very good dinophile. Even you can think about this type of systems, they are very nice with your nitrile, acrylonitrile. This type of systems are very good dinophile. These are good dinophiles. Right. So, these are the important things about your diene and dinophile. So, I said that in Diels-Alder reaction, if you take your Diels-Alder reaction, what you should first understand about your diene. So, we said that it should be electron rich and it should be in S cis conformation. Then we should understand about your dinophile. We said that it should be electron poor. And now we are going to talk about the conditions, which conditions will favor Diels-Alder reactions much better. Okay. So, to understand the conditions of Diels-Alder reactions, okay, we can get into the FMO theory, that is your HOMO-LUMO interactions. By knowing the HOMO-LUMO interactions, interaction, we can see which condition is much more favored for Diels-Alder, whether you can do a thermal activations or you can carry out your photochemical activations. Okay. First, we will see that in normal thermal activation, whether this reaction is favored or not. For that, how we do that? You basically you take your HOMO of your diene, so this is HOMO of your diene. Then we can consider the LUMO of your dinophile. So, we have seen the HOMO of your diene and LUMO of your dinophile. Now, they try to interact and you can see that orbitally it is nicely favored. So, this is on thermal activation. So, on thermal activation you can see that this reaction is, how you write this? You can write as pi 4s plus pi 2s. So, it is thermal activation, it is suprafacially allowed, Diels-Alder reaction. So, that tells nice that this reaction is on heating, it is suprafacial and it is allowed and the reaction goes very nice, okay, because it is geometrically as well as orbitally favored. That tells you your HOMO-LUMO interaction tells that. So, on heating we get a nice superficial to get our nice Diels-Alder reaction. Okay. This is the three important things we should know about Diels-Alder reaction, that is your character of your dyne which we studied, and then we studied how dynophile should be. Now, we are just seeing the condition of the reaction. The interesting part of Diels-Alder reaction is the selectivity. Okay. Diels-Alder reactions gives lot of selectivity, like we can talk about facial selectivity in Diels-Alder reaction, we can talk about exo-endo selectivity, we can talk about regio selectivity of a Diels-Alder reaction. So, we will do what we will do is that we will do one by one selectivity, we will try to understand them in detail. So, first we get into selectivity Diels-Alder reaction. So, the first part we will be talking about is the facial selectivity. Okay. If you take a cyclopentadiene with a transalkene, okay, I can think about two products. One I can say where your X is up, Y down, or another case I can talk about both in the same phase. Right. So, you can think about two products if you talk about facial selectivity, but in Diels-Alder the reaction is selective. So, you do not end up with this product, you end up with only the one in this. So, how to understand that part? We can see this reaction in two ways, like we can see them in the front approach or side approach and see how they make things to selective, how it gives selectivity. So, we will just see the front approach, see how we can look this. For example, I am taking a dyne, on A substituent, or another substituent A. Okay. Now, I can think about my alkene, one can be B. Now, if you just watch, if this is the front approach, okay. Now, what happens? It has only one way, okay. Your methyl comes up, these two methyls, and in this case 2 methyls goes away. There is only one way of orbital aligning together. So, you end up in writing a product A, get a methyl, one direction, and you can write this with your B on. So, you can look in this way, that is in the front approach, like how they come together. So, there is no change in chemistry. So, that is why they get much selectivity. You can see that in the side approach also, side way. It is easy for seeing that in some problems it will be easy to see the side approach, side view. You have an A here and it is your substituent, you have a same substituent and A outside. This is one way of looking into it, and you have an alkene methyl and you have B, another substituent, methyl B. Because this type of approaches will help you out in doing intramolecular Diels-Alder reaction. That time you can use this type of approaches. So, now what happens is that you can draw like that. So, your A will be outside and your B will be here. In this case, your A will be here and B, and then you can have your B. This way also you can look this. Okay. So, you can see in two ways. One you can see in the front approach, another by side approach. That is how because of this alignment we get selectivity in Diels-Alder reaction, and this is your facial selectivity. We see some examples, so that we see one or two examples and see how the selectivity is there. If I take an diene plus dienophile, okay. So, this reaction on heating, so you should think about the facial selectivity when you draw the product. So, you might end up with get a nice product like this. If same way, if I take the same diene and treat it instead of cis, if I treat it with a trans, so again you have a selectivity. So, you end up getting see this, that's why it is very important that you think about the facial selectivity when you write Diels-Alder reaction. Reaction is very stereospecific, right. So, you get like one type of products. That is your first selectivity about your Diels-Alder reaction, okay, facial selectivity. Now, what we will do is that we slowly get into your second selectivity, that is your exo-endo selectivity. So, I can take same way as cyclopentadiene and treat it with your anhydride, right. I can think of writing two products. In one case, I can have my anhydride away, be careful with your hydrogen, that is only tells the plane very nice. In another case, I can think about inside mostly like. So, I can write basically two products. Okay, one, this is this which is like away from the ring, which call as exoadact, which is inside, we call that as an endoadact. And if you see, if you carry out a Diels-Alder reaction, most of the time you have a selectivity across your endo product than your exo. So, we will find out, we will just look why it is, okay, why you get selectivity over endo. Just you can think about the transition state of this reactions, like I have a, I will just draw the transition state for my endo. And then I can write my so I have interactions, basically two ways of writing it. Just a minute, I will get you best way of writing that. Cyclopentadiene. So, it should be, this will be better way of facing down. So, I can have a link here, because if you see your double bond is here, and if you think about the cyclic transition state, what happens, you can think about like you will have a bonding here, right. So, you have a transition state across this and you have here, okay. This how you can look your endo, right. So, but if same way if you look your exo also, if I draw my exo, so, so both the ways you can say that it has been bonded, but the advantage in the case of endo across exo is that this is more the transition state. Here you have this secondary orbital interaction, okay, of your carbonyl with your alkene system. Okay. This is very important. You have a secondary orbital interaction, and this reduces the stabilize your transition state. Okay. In this case you cannot have that. That is why we say that the endo is as a selectivity across your exo when you talk about the Diels-Alder reaction. Endo is much more favored because of the secondary orbital interaction. You call this Endo Rule also. You can Endo Rule. What Endo Rule says, maximum accumulation of double bond on one side. Alright, it is nothing but maximum accumulation of double bond. So you can view in the case of secondary orbital interaction, or you can sometime you go with your Endo Rule, which says maximum accumulation of your double bonds on one side. So that is what your exo endo selectivity is. So when you take an exo endo, when you come across two products like exo adact as well as endo adact is much more selective because of the secondary orbital interaction and governs by the Endo rule. Clear? So, now we will get into another okay, before getting into another selectivity, we will just see interconversion of your endo to exo product. This is very interesting one. Okay, interconversion of your endo to exo product. See, so what we will do is that we will take our system which we are discussing, that is your similar system, we will take cyclopentadiene, same system. So, you can have your interactions here if you want, just trying to think about interactions. So, if I normally if you do this reaction in 20 degrees Celsius, okay, just take your thing and do it in 20 degrees. I am writing this way, okay, like you have a bonding here and you have a bonding here, okay, 20 degrees Celsius. What product you can really think about is so I can get an endo product, right. If I take this reaction and just do it in 20 degrees Celsius, as earlier case we said that we have a secondary orbital interaction. So, the reaction will give me the endo product. Now, what happens is that once you get an endo product, if you take the product and heat it to 120 degrees Celsius, okay, the interesting fact occurs that you end up with an exo now. So, you have an endo adduct and this endo adduct, if we heat it, it converts itself into exo adduct, very interesting. But the same reaction, for example, if I take my cyclopentadiene okay. I do not get this product. If I take my cyclopentadiene with my anhydride malic anhydride and I do the reaction, I never get my exo adduct. But if I take the reaction, do it by 20 degrees Celsius, I end up with my endo adduct. But if I take my endo adduct and heat it, I end up with my exo product. So, what this says? This says very clearly that the endo adduct is kinetically controlled, because that is preferred once you do the reaction. It is kinetically controlled one, whereas the exo is thermodynamical stable. So, that is a very interesting point to know about your exo and endo. So, endo is that it is kinetically favored because the transition state stabilizes. So, the reaction wants to give you the endo, but once you heat, endo gets flipped to your exo, saying that exo is thermodynamically stable one. Clear? So, that is more important part of your exo and endo. So, we have seen selectivity, now we see the interconversion of endo to exo. Now, the another selectivity which we are going to talk about is your Regio selectivity, which is which also occurs in Diels-Alder reaction. So, what happens is that I take a diene, betadiene with my methoxy substituent. Okay. In another case, I take with an electron withdrawing dienophile with a cyano substituent. Now, I can write two products again in this way. So, one over me. See, if this are going to form like this Diels-Alder reaction, I have my cyano here, or if it is inverted, the dienophile have cyano. Okay. See, we call them, because it is not an aromatic system, still that is why we call them as a pseudo ortho. Okay. Can call as pseudo ortho. In this case, we can call them as a pseudo meta, because aromatic system only we use the word ortho and meta. Since anyhow, for understanding, we can call them as ortho, this ortho substituent, and in this case it is a meta substituent. You can think about both. Okay. But if you do the reaction, you have a selectivity across your ortho, you have a selectivity over this. Same way, if I take a methoxy with a similar system, cyano, okay, methoxy and cyano. Again, I can think about writing two products for this. In one case, you get para, in other case you end up with a meta, right. So, if I do this reaction, the selectivity is over para. So, when you do a Regio selectivity, that is, if you take this reaction, you end up with a pseudo ortho or meta, or you end up with a pseudo para or meta. If you generalize, you can come to a statement saying that electron donating and electron withdrawing substituents with respect to the product. Okay. Electron donating and electron withdrawing substituent arranged prefers to arrange in pseudo ortho or pseudo para position to each other. So, that you can do this generalization. So, your electron donating and electron withdrawing substituent in the product, what I am meaning is that the electron donating and electron withdrawing substituent most of the time in the product prefers to be in the either ortho or para. You never get, you have selectivity over this two, over meta. So, that is what I said, electron donating and electron withdrawing substituent arranged in pseudo ortho or pseudo para position to each other. Now, we will understand how it happens, why this things happens. Okay. It is very easy, you can see from the mesomeric structure of this, you can understand them. Okay. For example, I have this system. Okay. Just we can write the mesomeric form of it. Minus you can end up like this structure. So, this should be your positive minus positive. Yeah. Now, you can have this nice interaction, right. So, you can just have your flow of electrons in the mesomeric structure. This side it is electron withdrawing, this is electron donating. So, you get a nice type of structure, and based on this you can think that it goes for it prefers to be in the ortho position compared to meta. Just by drawing the mesomeric structure you can find out, and that tells the reason. Yeah, it is more about selectivity. You get the products. Okay, when you do a reaction of Diels-Alder, you always end up with 75-25, but 75 will be your ortho and 25 will be your meta. It is not like specific. Okay. You do not get only one product, you get both the products, but selectivity is across ortho or para. Fine. Okay. Similar to extension of this, if you see, we have Lewis acid. If you do a Lewis acid catalyzed Diels-Alder reaction, so basically, like if you take a reaction of a diene like this with an aldehyde, kind of, oh sorry, it can be an acetone. Okay. If you do this reaction, you should get two products, right. If you take the Regio selectivity you are talking about, so I should get one should be in the para position and one should be in your meta. So, I should think about two products, and if you do this reaction, yes, exactly, if you do it at 120 degrees Celsius, just you put this two and heat it, you end up with two products, but if you see the selectivity, it is 71:29. Okay. But same reaction, if you do it in tin chloride, for example, the same reaction, if I do it in SnCl4, yeah, sorry, tin chloride, SnCl4 in tin, any Lewis acid, okay, SnCl4, sorry, at 0 degrees, just at 0 degrees Celsius. You end up with 93:7. So, you have a increase in the selectivity. Yeah, you can easily understand why it happens, because like you in the case of your dienophile, now your Lewis acid goes and binds with your dienophile. So, it can withdraw the electron much more better than earlier case. So, you end up with a nice increase in selectivity. That is just because of your binding of your Lewis acid to the dienophile and makes it stronger electron withdrawing group. That is why the selectivity is increased. Very important when you do Lewis acid catalyzed by Diels-Alder reaction. So, what we did is that, So, we took Diels-Alder reaction, we said that dienes are diene is important. So, we said how the diene should be electron rich one, and your diene should have a S-cis conformation, okay, to do a proper Diels-Alder reaction. Then we went to dienophile, we said your dienophile should be electron poor. If it has an electron withdrawing group, it is well good, it becomes a very good dienophile. Then we slowly went to the condition, and by using your HOMO-LUMO interaction, we said that by thermal activation it is supra allowed and the reaction goes nicely. And then we saw 3 selectivities. We studied facial selectivity, okay, and we went to exo-endo selectivity. We said endo selectivity is good because of its secondary orbital interaction. Then finally, we went to the Regio selectivity. We said that the the electron withdrawing and electron donating substitution should be in the pseudo ortho or pseudo para. That product is much more favored compared to the meta one. So, that is about your Diels-Alder reactions. We will try to study Diels-Alder reactions about the reactivities of dienophile, dienes, then intramolecular Diels-Alder reactions in the next class. Okay.